Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
I want to welcome you all to today's meeting, today's discussion. The topic today is challenges in firing ceramics. And it's really solving problems there are two kinds of problems that you have when you fire ceramics. There are problems when you're doing a firing that result actually in defects on the wear. And there are also problems that you can have firing that really may or may not show up on the wear. It's just a problem maybe with operating the kiln. So that's what we're going to talk about today. There are and as you're probably aware, there are other sources of defects in ceramics, not just the firing, but the clay can also be the origin of defects in ceramics, as well as the glaze. So all of these things can interact to produce a defect. Before we get into that, I just want to mention next month's topic. Next month's topic is going to be about simple math calculations that you use in the pottery studio. And we're not going to go into some of the in-depth calculations like converting Seeger formula to a regular recipe, because there are computer programs available for those, and just about, I don't know anybody that does them longhand anymore. I used to do them longhand, but it's tedious. But there are a lot of simple ones that you can use that just use everyday examples. An example would be, for instance, if you don't have enough of an ingredient to make a recipe, but you still want to make up the recipe, how can you adjust the calculation so that you can use up all of that small amount that you have and still make up the balanced recipe? Things like that. So we'll talk about, that'll be next month's topic. Okay, so challenges in firing ceramics. Let's talk first about kiln performance problems, because there are two different, as I mentioned, these two different categories. The performance where the kiln you may have a problem just with the firing, and it may cause a defect, or it might not cause a defect, but it's still a problem with the firing. Today's session is kind of a wrap-up for what we've been talking about the last 3 months. We did a series where we talked about, for 3 months, we talked about the three main kinds of firing. First, we talked about wood firing, and we talked about gas, and we talked about electric. So I thought this would be a good wrap-up session to bring all those issues together and talk about problems that are common in some cases to all three types of firing and how they result in defects that we see in the pottery. So problems related to kiln operation. This is up here just sort of as, I gave this talk about 10 years ago at a conference out in Front Royal. So that's when I had these prepared, because it was a large hall. And so I wanted, this way people can sort of follow along what we're talking about. So first I'm going to talk about electrical kiln firing and just some common problems. One of the problems, again, this is thinking about the operation, not so much about whether it causes a defect directly anyway. So one of the common things with electrical kilns is a non-uniform temperature distribution, typically from top to bottom, but also radially. That it's fairly common on a larger kiln that the outside of the shells will appear to be hotter than the center of the shells. Well, the cause of this, if you don't have a downdraft fan in an electric kiln, you know these new fans where they pull the air down, then it's very normal to have the top of the kiln to be very often at least a cone hotter than the bottom of the kiln. This is just due to natural convection. The hot air and hot gases rise, and the kiln tends to be hotter at the top. Another cause of the non-uniform distribution can also be aging elements, is that even aside from the convection, if one of the elements, especially on the bottom, for example, isn't functioning properly, or it's not heating up as much, that even adds to the temperature gradient that you get, because the bottom, because of the elements, the bottom isn't getting as hot as the top. And another feature that can contribute to that is also the way you stack the kiln. If the kiln isn't stacked properly, then you can even compound that thing. Especially if you have a downdraft kiln, if you don't have one, you don't want to put closely spaced shelves at the bottom. Because again, in that case, the kiln is tending to heat up not as readily on the bottom. And if you have closely spaced shelves, they heat up even more slowly. So if you don't have a downdraft fan and you put closely spaced shelves at the bottom, you're going to exaggerate the temperature difference between the top and the bottom. So it's a good idea, in that case, to put some open shelves at the bottom, again, if you don't have the fan. The nice thing about these downdraft fans, aside from the fact that they get the fumes out of the kiln, is that they really even out the temperature profile. With one of those fans now, there virtually is very little difference in temperature now between the top and the bottom of the kiln, because it's very gently pulling the hot gases and the hot air down through the bottom, so it evens it out. Another common problem with electrical kilns is corrosion of the bricks and the metal. And this is actually due to the fumes given off from the clay. I've got some good examples here. The fumes given off from the clay and the glazes when they're fired. And one of the main types of fume that comes off is sulfur oxides from impurities in the clay. And when they meet the air, they form sulfuric acid. This is the same kind of acid you have in your car battery. It's a really strong acid. And it eats the metal, it eats all the metal parts that it's supposed to, and it actually attacks the brick. And I've got some examples here I can pass around. This is the thermocouple. This is the end of the thermocouple. And this was just a fairly common type K thermocouple that's present in a lot of kilns. This is the bead, the part that would stick into the kiln. And if you look at it, you'll see that the wire is very, compared to, these are the wires sticking out the back end. Compare the thickness here to the back end, and you can see that the wires have basically been corroded. They've been eaten by the fumes in the kiln. And at some point, this was removed because at this point the thermocouple wasn't working properly. But the wires are basically being corroded and just eaten away by the fumes in the kiln. And here's another example. This is the tube. You may recognize it from a kiln sitter. And this is the outside where it mounts on the kiln, and this is the part that sticks in. The ceramic tube was actually attacked by the acid in the kiln, and you can see the rust, the fixture that held it into the kiln was completely rusted away, and the ceramic tube was actually attacked. And again, the reason why this is in this location is because this is where this is on the outside of the wall of the kiln. So this is where the acid fumes from the inside of the kiln met the air on the outside of the kiln, and the air has the moisture in it. So right there, where the gas and the air met, it formed the sulfuric acid, and it just ate away the ceramic and just completely ate the metal, right, the supporting metal that holds it. So the corrosion is really not likely to result directly in any kind of defect, with one exception that I'll show you in a minute, any kind of defect on the pots, but it's certainly going to affect the operation of the kiln. Like in this case, the thermocouple wasn't operating properly because of the corrosion. So the thermocouple failed because of that.
And did that happen over time?
Yes, over a long period of time. Yeah. And this is an example. This is a bare thermocouple because these are the wires. A lot of thermocouples have a protective ceramic tube over them, like a little test tube, and it shields the thermocouple from the fumes. So this is a combination of, this is the less expensive type of thermocouple. This is the type K, which is not very resistant to fumes, and it didn't have the protective tube over it. And a lot of thermocouples now have, a lot of the kilns come with, if you look inside your kiln, if you have a newer kiln, they have a closed end tube which protects the thermocouple from some of the fumes. So this wouldn't be as likely to happen. One of the defects that can happen from this corrosion, though, is this. This is an example of a little dish that was sitting on a shelf underneath the thermocouple. And when the thermocouple corroded, chunks of the oxide landed on the pot. So they fell down, and because the thermocouple was hanging over the shelf. So these are little bits of the metal that fell off the thermocouple. Yeah, some big pieces fell, and they landed right on the glaze and ruined the pot.
Is it a problem to touch it?
Pardon?
Is it still active acid, or has it like reacted and is it?
No, it's just it melted into. It was basically iron oxide, the oxides of the metal. It was the rust. It was essentially the corrosion products from this. They fell off and landed in the glaze and got stuck in the glaze. Oh. So there's a case where, a rare case, but there's a case where the corrosion of the metal actually caused a defect in the pot that happened to be sitting underneath the thermocouple.
Is it okay to touch those?
Yeah, sure. Yeah, because they're not acid anymore. It's long since been neutralized.
If we're in our own kiln and this happened, should we avoid touching it?
No, because I've never seen it to the point where it actually condenses on the surface. Usually, because it's like a sulfuric acid gas or mist almost. So I've never seen it where it's actually wet or anything like that. And usually,
if it's wet, don't touch it.
Yeah, if it's wet, don't touch it. But it wouldn't. Chances are it wouldn't be wet. It's not that concentrated. But over a long period of time, it definitely, it has an effect on the brick. The other thing you'll see on the bricks is, and it's kind of strange, but on the kiln, when the fumes leak out and they leak through, because the bricks are porous, right? It's a soft brick. So the fumes come out through the brick, and they don't actually attack the brick. until they get to the outside of the brick. You might think, well, the fumes from the inside attack the inside of the brick. They don't. They attack the outside of the brick because that's where the fumes go through the brick, and then they meet the air from the outside that has the moisture in it. So it's when the sulfur gases meet the moisture in the air that the sulfuric acid forms. So I've seen old kilns, and you see it a lot of times when you lift the lid, the outer portion of the brick right against the metal shell looks kind of crumbly. That's from the acid attack. Because it's essentially eating its way in from the outside where it meets the moisture.
What causes more corrosion, glaze fires or bisque fires?
Bisque firing, I'd say offhand, because that's where you're really essentially you're cleaning up the clay. You're getting rid of a lot of the carbon and a lot of the sulfur, like the minerals, the sulfur minerals in it. So I say in general, it's going to be the bisque. Unless you're firing glazes that contain a lot of sort of potentially corrosive materials in the glaze, but I think more than likely it's the bisque. Another problem with electrical kilns I put as sitter timing is basically if you're using the kiln sitter to actually control your firing, which you really shouldn't, but the kiln sitter can shut off too early or shut off too late, and there are a lot of ways that a kiln sitter can be improperly set up. It really was, to be honest, it was never made to actually run a kiln firing. It was made as a safety device, as a backup, so that if the kiln didn't shut off, and let's say as a potter you weren't there, you had to leave or something like that, that the kiln wouldn't just keep going and melt down, the kiln would shut off. But they're really not precise enough to actually control the firing. You should be firing with a cone pack, but they were made as a backup. But a lot of people still use them as an actual way to control the firing. And the problem with in a lot of cases is, even if there's nothing accidental that happens, is the kiln sitter may be out of adjustment. And there are different ways that you can actually, there's a certain angle at which the little rod on the top of the kiln sitter, there are like two supports, and then there's a rod that drops down. There's a certain point at which the kiln sitter is supposed to shut off the location of the rod relative to those two supports. And if you got the kiln new, there was a little, I'll pass this around, there was a little gauge that came with the kiln, and this is actually used for adjusting the kiln sitter. And I was telling Dennis earlier this morning, a lot of times when you buy a new kiln, this comes shipped on the kiln sitter, and people think it's just a packing device and they throw it away. Where actually, this is the gauge that you use to adjust the kiln sitter. So it comes shipped on it so that it doesn't bounce around, but you need to save it. And if you look at this, you'll see there's a hole and then two holes in the side. That's meant, the idea is you slide that over the rod and the two prongs that support the cone, and then you make an adjustment on the outside so that when the rod is in that position, that's when it shuts off. So you can adjust the sensitivity or the position when the kiln sitter shuts off, how much the rod bends when it shuts off, and this is how you do it. So if you haven't seen one of those before, I think you can still buy them as a separate thing, but they come with every new kiln sitter. And I know a lot of people just, they thought it was part of the packing, so they threw it away. So, and one of the other, aside from the fact that the kiln sitter should be adjusted so that there's a certain amount of movement when it shuts off, a lot of other things can happen. The cone, for example, if you put it too close to the end of the porcelain, when it'll get slightly soft, it'll actually stick to the end of the porcelain and then it doesn't move. Or sometimes what happens is, after a while, the parts of the kiln sitter that stick in get corroded from the fumes, and then when the cone starts to soften and melt, it also sticks to those and it doesn't move. So a good trick that helps with that is you should put kiln wash on your kiln sitter. If you have a little bit of kiln wash, you should paint the under part of the rod and the blades with a little bit of just a thin coating of kiln sitter, so that when the cone starts to melt or get soft, it doesn't stick in place, it can slide, because it has to slide down in order to bend. So it's a good idea. Touch up the kiln, the ends of the points with a little bit of kiln wash. Okay, let's go. By the way, I wanted to mention also, if you have any questions as we go along, please jump in. This is, or anything like either issues that you've had, or if you have any questions about anything, don't hold back. So let's talk about fuel-fired kilns, and I've lumped together under fuel gas kilns and wood kilns. In some cases, some of the issues are common to both. In some cases, I'll point out it might be just a wood kiln or just a gas kiln, but they're in a different category than electric kilns. And one of the common firing problems with a fuel-fired kiln is a slow temperature rise. And this could be gas or wood. It's more common with wood because gas, essentially, if you're not getting a fast enough temperature rise, it means you're not burning enough gas, so you turn up the gas. That's one possibility. But with wood, you have other issues involved, like the size of the wood. If you're heating and you're putting in pieces of wood that are too large, they tend to burn slowly, and so you don't get the quick heat coming out of the kiln because the pieces are simply too large. So the size of the wood can play a role in how quickly the kiln is heated up. If the wood is damp, that can also play a role in it. If the wood is damp, it takes extra heat to drive off the moisture, so the damp wood is not going to allow the kiln to heat up as quickly. Also, another factor is you may not have enough air coming in. You can put all the wood you want in the world in the kiln, and if you don't have enough air and enough airflow, then the wood can't burn fast enough, and you can't produce enough heat. Related to this also is the next problem is stalling, and this is a fairly common feature in both gas and wood kilns. People report that when you get up to around 2,000 degrees, give or take 100 degrees or so, the heating rate tends to slow down, and sometimes they'll blame it and they say, oh, something's going wrong. That may be true, but a big part of it is this is a very natural effect. It's kind of a fundamental law of physics and heat transfer that the higher in temperature you go, the higher you heat something up, the faster it wants to cool off. And when you get up to about 2,000 degrees around in that neighborhood, even though you're pumping a lot of heat into the kiln is trying to cool off really fast. It's giving off a lot of heat. So it's kind of like climbing a hill, and as you're climbing the hill is getting steeper. That's the effect you're firing. So that as the kiln is getting hotter, you can't just put fuel in at the same rate that you have all along, because the kiln is losing heat at an ever increasing rate. So you have to speed up the rate that you're increasing the fuel, because the kiln is losing heat faster as it gets higher in temperature. So this stalling is a natural effect. People, they sort of establish a certain rate for the gas or a certain rate that they're putting the wood in, and when you finally get up to a certain temperature, roughly 2,000, it's no longer enough fuel because the kiln is losing heat so fast. So you have to increase the amount of fuel you're putting in. That's a very natural effect. That has nothing to do with the kiln necessarily or the way you're doing it. That's just a natural effect. So that's the natural heat. The natural heating rate. But so the way to overcome that is you have to put in more. You have to burn more fuel. You have to overcome that heat loss. So you have to turn up the gas. You have to increase the stoking rate or change the size of the wood or the amount of wood. Effectively, you have to burn more fuel to overcome that. And it's a little easier with gas because you just turn up the gas. But with wood, you have all these other factors: the size of the wood, the type of the wood. Even for instance, like softwood, like pine, burns faster and hotter than hardwood, for example, than oak. So even the type of the wood can affect how quickly you're going to get the heat from that amount of wood. So it's a little more complicated with a wood-fired kiln. Another problem, as I show here, is poor reduction. And this applies to both gas and wood, is that if you're not getting good reduction and you're trying to get reduction, is you have too much air. Getting reduction in a kiln is a tricky balance between getting enough air in the kiln to burn the fuel so that the temperature keeps rising, but not so much so that you're burning the fuel completely, because the reduction atmosphere is produced by incomplete burning of the fuel. It's the carbon monoxide from the incomplete burning. So you don't want a lot of air so that you completely burn the fuel. Then you don't produce enough carbon monoxide and you don't get good reduction. So it's a tricky balance between maintaining just the right amount of fuel and just the right amount of air, the balance between the air and the fuel. So the temperature keeps going up, but it doesn't go up as fast as it could, and you stay in reduction. And again, that's a little easier to maintain steadily in gas than in wood. In wood, you tend to cycle. When you're firing a wood kiln, you put a load of wood in, and it tends to go into very heavy reduction, which is typically when you get the heavy black smoke coming up the chimney, really heavy reduction. And very often the temperature, if it doesn't stop climbing, might actually decrease a little bit, because at that point, you're not burning much. Then the wood catches, and then the temperature starts going up, and then you go into a lighter reduction. In gas, you tend to, it's easier to maintain sort of a constant level of reduction and a steady temperature rise. But in wood, you're constantly going from heavy reduction to lighter reduction, heavy reduction. Every time you stoke and you throw a bunch of wood in, until that wood catches, there's not as much burning, so the temperature starts to decline or at least level off, and you go into really heavy reduction because you're really choking. And then the wood catches, and then the heat comes out, and then you go into lighter reduction. But it's basically, it all comes down to balancing the air and the fuel. Excessive reduction I've got here is that you can actually get too much reduction, and that's inadequate air. So this still goes back to the same issue of the balance between the air and the fuel. And this is especially true in gas. It's possible, and we'll talk about this when we come back onto defects. This can cause a defect. In addition to being a firing problem, as we'll see later on, it can also cause a defect. If you go into too heavy reduction early on, in a gas especially, you don't want to make soot. Soot in general. Soot doesn't do anything for you. It isn't contributing to the reduction. It means you've gone into too heavy reduction. And in some cases, that can actually cause defects in the pottery. One of the ones is black coring, for example, and I'll show you some example later on. But the problem is, if you're going into too heavy reduction, then in a sense, you're wasting fuel. You're putting a lot of fuel in there. You're not burning enough of it to get a good temperature rise, and in addition, you're getting soot, which really isn't helping you. So it's very inefficient burning, if nothing else.
Is the soot, are those like, is that gas or are they solid? I mean,
It's little solid carbon
so
particles.
It can't react, that's why that.
Well, yeah, there isn't enough. There simply isn't enough. You're breaking down the organic compounds in whatever the fuel is, and you're breaking it down to carbon, but you're not reacting the carbon then to produce carbon monoxide or carbon dioxide. You're just making carbon.
Yeah, okay.
Because you've got really heavy reduction. If you had more oxygen, it would all convert to carbon dioxide or carbon monoxide.
Why can't the carbon itself, like?
There isn't enough air to react it. This is the same reason, like you get soot out of a candle, when you hold your flame. Okay, it's the same thing. A candle flame, you get air coming into the center, the outside of the flame, but there's still a portion of the flame in the center that isn't getting enough air, and that's one of the sources of the soot even though it's out in the open air, you still get soot off a candle flame. That's why, because there isn't enough air getting into the center to burn all the carbon to convert it to carbon dioxide.
Wouldn't it just more effectively grab it from the glaze?
Pardon?
Wouldn't it just more effectively grab it from the glaze or clay?
What, the oxygen?
I mean, yeah.
It's not free oxygen. It can't actually. It doesn't actually. It's not that instantaneous that it can actually just extract it from the clay. Because in other words, it would have to extract it almost instantaneously, and it doesn't happen that easily. It's not that simple.
I mean, I guess I'm wondering why carbon monoxide does it and not soot, not carbon. When carbon seems like it would be more hungry.
No, but actually, carbon monoxide is very active chemically, and it's a very active oxidizing agent. Okay. Hot and cold spots again are related to the same kind of thing in the kiln. If I'm not getting good mixing of the gas and of the fuel and the air, then I may have like streams of air going into the kiln, and I may have places where I've got fuel going into the kiln with not enough air. So where I have air going in, I may be getting better burning, and I might get a hot spot. And if I have another place where I have just fuel and not enough air going in, not good mixing, then that could be a cold spot. So again, it goes back to things like the hot and cold spots could be poor mixing of the fuel and the air, poor circulation or flow. This could even be part of the kiln design. If I don't have, or even the stacking, if I haven't provided a way for the gases and the fuels to move throughout the kiln and hit every part of the kiln uniformly, then I'm going to have certain areas that maybe get more exposure and less, and that can also contribute to it. And part of that is the stacking, not just the kiln design. It's the stacking. Have I created pathways for the flames? Because in either case, gas or wood, I've got flames moving through the work. Have I provided pathways for the flames to reach all the parts of the kiln? And with poor stacking, I could be blocking off certain parts. Another problem related to fuel firing is not, and I've mentioned this already a little bit, is non-uniform reduction, not just hot and cold spots, but non-uniform reduction. And that's related to the same thing, where I don't get good mixing of the gas and the air, basically. And the last point I just mentioned is I have half gas use. That could also be high wood consumption. So do I seem to be using a lot of gas or a lot of wood, a lot more than what you might think I need to fire the kiln? And basically, that goes back to the same thing, not a good balance between the gas and the air. If I'm burning too much wood, I may be getting temperature rise, but I'm using the wood or the gas very inefficiently. So that still goes back to like gas and air control, the proper balance and then the proper mixing so that I'm burning the fuel really efficiently. I'm not wasting wood by not burning it efficiently. Any questions on that? Okay, so let's talk about problems related to kiln design. So this was operation. This is things you're doing while you're actually running the kiln. In some cases, there may be features of the kiln itself that you're fighting against that you may or may not be able to overcome. So let's talk about electrical again. An inadequate bisque. And by that I mean a bisque where the work, you're doing a bisque firing, and the work basically is under bisqued, so that maybe you get pin holding later on when you're doing glaze firing. One of the problems I've seen with this is when you're using the canned programs, the programs that are built into the electronic controller. In some cases, with the clay you're using, the programs may not be adequate. Like they may be too fast or they may be too short. When they set up those canned programs, usually there are three. There's like a slow, in some cases there's a slow and a medium and a fast rate, and then you can do a bisque. But they're still meant to be sort of an average overall, it's an average program. They can't cover all the possibilities. Well, you might have a clay, for example, that's really dirty. And in order to bisque it, you might have to do a much longer and slower and maybe even a slightly hotter bisque to really clean up the clay to get all the impurities out of the clay. And that standard canned program simply may not be good enough for it. And I've seen that situations where people are using, they're either using local clay, let's say for local earthenware, and they're doing it low fire clay, and they simply can't get it clean. They do one of the canned programs, and it simply isn't long enough or slow enough or hot enough to really clean up the clay. In which case, then you need to either write your own program or do it manually to modify it for your particular clay.
It's also, because it's canned, you can't soak at various temperatures to help.
Yeah, you can't. Yeah, it's just you're using the right.
And sulfur and all that get burned out.
Right, and so there might be a point where you need to hold it to really. And with the clay you're using, the only way to find out is you find it out. And so in that case, the canned program is inadequate. And I've seen that happen where people, they say, well, I used the standard program. Well, in that case for their clay, the standard program wasn't appropriate. They needed to modify the program because they were using not your typical average clay. Underfired or overfired glaze, and this again, the main reason I've seen, especially. And again, underfired would just mean that, again, they might have a glaze where the program isn't, it's not, maybe you need to hold, so the standard program, again, doesn't have all the features to adequately allow the glaze to mature. But especially overfiring, this is a fairly common thing with electric kilns, is that if you fire on a fast schedule with an electric kiln, when you're firing to a certain cone, the faster you fire, the higher the actual temperature is when you reach that cone. Which sounds strange, but because cones are sensitive to time and temperature, the combination of that's what cones respond to. So if I have less time, then in a sense I need more temperature to make the combination work the same for a cone. And I'll pass this around. This is a good example. This was a pot that was in a cone 6 firing, and you'll see that the front side that faced the elements is all overfired and blistered, and the back side is just fine. And this is because this was on a fast firing, and so the kiln got too hot. The outside, and 20 degrees and it might be 20 degrees difference or something in that neighborhood. That's a lot for some of these glazes. And so the one side of the pot got overfired where the side facing away from the elements was okay. And this was because this was on a fast firing, so the problem was because it was fast, the outside of the pot got a lot hotter than just the other side of the pot. Instead of firing it more slowly, where the whole pot could increase in temperature gradually and stay the same temperature, there was a big difference in temperature between the two sides of the pots. And the answer to that is just slowing it down. I see this effect a lot, especially in schools and in community studios, where there's a lot of pressure to get a lot of work through quickly. You know, you have a lot of pots and a lot of people, anxious potters, waiting for their pots to come out of the kiln. So they tend to fire the pot, they overload the kiln, and they tend to fire the pot too fast. And so actually then you don't get good mature. You need to slow it down. It also comes from the basic geometry of an electric kiln. When you think about it, an electric kiln is only heating from the outside of the load. You have this stack of pots, and the heat is only coming from the outside. So you have to allow enough time for the heat from the outside to get all the way into the center and hopefully not overheat what's on the outside and underheat what's on the inside. So you can't, if you go too quickly, you get this big temperature difference between the outside and the inside. So the outside pots can be overfired and the inside pots can actually be underfired. So the solution to that is slow down. Slow down and allow, if you think about it, if I have a whole shelf full of pots, the only way the pots in the center can get hot is by having the pots next to them get hot and then radiate the heat to them. So the heat is essentially traveling in. It's not like in a gas kiln or a wood kiln where you have this river of flame moving through the pots that brings the heat to them. This is just by radiation from the outside.
But isn't your exhaust fan moving it around pretty good?
No, because the exhaust fan, it's not supposed to create a wind tunnel. It's just very gently pulling the air down to the bottom. I mean, it's not like zip. It's just very gently pulling, just enough to pull it out, just to keep the air moving. It's not creating, so it does, it is pulling the air down and making the bottom, a little warmer, but it's not really like a circulation fan.
And just 20 degrees?
20 degrees is enough on a lot of glazes. And this is especially true, I found, with commercial glazes. Commercial glazes tend to be more temperature sensitive because of the way they're formulated than some of the glazes you can make up. If you make up the glazes from your own materials, you can formulate the glazes that have a pretty wide temperature range. I have a cone 6 white glaze, sort of a glossy white, that works great at cone 6, and I've taken it up to cone 14, and the same glaze works just fine. Whereas a lot of commercial glazes, they use a lot of frits. They tend to be more narrow temperature range, and half a cone or even a cone more is enough to make them either nicely fired or overfired or underfired. Let's see what else we had. Non-uniform temperatures, again, distribution with electric, and this can cause this is the reason why this is related to a thing is to the kiln design is if you only have one thermocouple in the kiln, then it's only sampling that one point in the kiln. A lot of times kilns now, and there's nothing wrong with this, but you have to keep it in mind. A lot of the kilns now, for instance, have 3 thermocouples, top, middle, and bottom, and they're balancing the temperature between those two. So the controller is automatically sensing if there's a difference, and it compensates for it. You have to keep in mind that if you have only one thermocouple with a controller, and again, there's nothing wrong with that, but you have to keep in mind that it's only sampling that one point. So when you're loading the kiln, don't have the part of the kiln that's near the one thermocouple be very different than the rest of the kiln. For instance, don't have a very wide shelf by the thermocouple and very narrow, closely spaced shelves everywhere else, because that wide space is going to heat up faster. It's more open, it's going to heat up faster, and the thermocouple will sense that it's heating up faster, and so the other thin, closely spaced shelves will be underfired. So just keep that in mind, that with only the one thermocouple, it's only sampling that one little part of the kiln. Okay. Problems related to kiln design with fuel-fired kilns. Again, so now we have this. Now this is design, a slow temperature rise or difficulty reaching maximum temperature. This is kind of like what we talked about before, but in this case, it could be actually related to a feature of the kiln. For instance, on a gas kiln, the gas burner simply might be too small. When you're firing any kind of a kiln, one of the sources of a lot of the waste heat in the kiln is you have to heat up the kiln. If you think about it, ideally, if you're firing a kiln, what you'd like to do is only heat up the work and nothing else. That would be the most efficient thing. If you could somehow not heat up the shelves and not heat up the kiln and just heat up the pots, that would be super efficient. Well, you can't do that. And as a matter of fact, for a typical efficiency, when you talk about how much heat is actually going to the wear of a gas kiln or a wood kiln, is somewhere between 5 and 10%. 90 to 95% of the heat is wasted, meaning it's heating up the kiln, which doesn't do anything for you. It's heating up the shelves or it's going up the chimney, it's wasted. So, but one of the things that can happen is, since I have all these other parts of the kiln that I have to heat up, if the burners are too small, then the whole, in order for the work to get to high temperature, the whole kiln has to get to high temperature. So if the burners are too small, I simply can't get the rate of temperature increase that I want. Or if it's a wood-fired kiln, for example, the firebox might be too small. When you're building a gas kiln, part of the important feature is to make sure your burners are adequate for that volume, that size of kiln, or even for the type of bricks. If you're building a kiln that's all constructed out of hard bricks, you have to have more heat input to the kiln than if it's built out of soft bricks where they're insulating and they won't waste as much, they won't absorb as much heat. So you have to take those factors into consideration when you're building the kiln. Similarly, if you're building a wood kiln, you have to design it so the firebox is big enough that it can produce enough heat to heat up the kiln. So those are structural elements or parts of the kiln design actually that can control it, aside from the way you operate it. Another feature can be the air inlets can be too small. Whether it's a gas kiln or a wood kiln, you have to provide enough inlets for additional air to get in to burn all the fuel. So for instance, if you have gas burners and the holes in the side of the kiln, I'm assuming these are Venturi burners now, not forced air burners. But if the holes in the kiln are too close to the size of the burner and sufficient air, additional air, can't get in around the burner, then you won't get enough air to burn all the gas. Or if in a wood kiln, if you don't have adequate air inlets into the firebox to burn all the wood, you won't get adequate burning. So that's a design, that's hard to change once you've built the kiln. It's hard to increase the air openings. So that's part of the kiln design. Another feature, the reason why I'm talking, this is a very common problem with fuel burning kilns in terms of the kiln design. There are a lot of kilns that are built poorly designed, and from the start, they've done something to the kiln to create a kiln that's going to be difficult to fire. Another feature of this is the exit flue opening is too small. At the back of the chamber, where the chamber is going into the chimney for a gas kiln or a wood kiln, if that opening is too restricted, then it can't draw in enough air and it can't burn properly. So all of these, especially since a lot of gas kilns and almost all wood kilns are owner built, they're built from scratch, these are all design features that are really important to consider when you're building the kiln. It's not like you buy a commercial kiln. If you buy a commercial like a gas kiln, they've done some of these calculations and they figured in the size of the openings, but it's very common to not have that done when if you're building your own kiln. Another contributing factor is the chimney could be too short. If the chimney simply isn't tall enough, then you don't create enough draft to pull in enough air to burn all the fuel, and you can't get a good temperature rise. So a lot of, as I say, for gas and wood kilns, there are a lot of features that are a basic part of the design of the kiln that are important considerations to make sure that it's going to fire properly when you get around to firing it. Okay, another problem, low gas pressure. And this when I say kiln design, this is part of the complete equipment for the kiln, is the gas tanks may be too small. As with propane, as you're probably aware, in a gas tank is actually liquid in the tank. And then when you open the tank, the liquid evaporates and produces the propane gas that you're using. Well, if the tanks are too small or the level of the gas in the tank is too low, there's not enough gas there that can boil quickly enough to produce enough gas. So you simply can't generate enough gas from the tanks to get the heating rate that you want. So with propane gas, it's generally, you generally want to oversize the tank. You never, for instance, with propane, you never run the tank down to empty. When the tank starts getting low, maybe down to about a third or even more than that, it's time to refill the tank because there isn't enough gas left in the tank to boil and produce gas fast enough. So if the tanks are inadequately sized, you at some point, and the level starts getting low, you won't be able to get the heating rate you want because you're simply not being able to produce enough gas. And finally, the last one I had here is oxidation during cooling. Is that when you finish firing the wood kiln or you finish firing the gas kiln, you want to shut up the kiln completely tight and not let any air in, because as the kiln cools down, it will tend to draw air into the kiln. And if there are particular holes or spots where the air can leak in, and they happen to lead to a pot, you get a little jet of air or a stream of air going in and hitting a hot pot, and it'll reoxidize the glazes.
Can you close up the space around the Venturi burners?
Yeah, normally what you do is you pull the burner back a little bit and you put a plate, like a piece of kiln shelf or something, and you completely block the hole, which is another reason why it's a good idea. You don't want the burners right up to the face of the kiln. Sometimes they're fixed, but you leave a little space there so that you can slide something in there and completely block it.
Out here, can you do that out here?
On our gas kiln? Yeah, I can shut off. Well, I can't shut off the burners on the bottom. I can't get at it, but I can completely block the top.
Right, okay.
And since it's an updraft, basically, if I can block the top, then it doesn't draw in any more air.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for The Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.